Welcome back. In yesterday's video, I introduced you to a skill called linearization, where we found the equation of a tangent line, and we used it to approximate a curved function. Today, in lecture 4.5b, we're going to see another application of drawing tangent lines. It's called Newton's method. By the end of this video, you should be able to use Newton's method to find the roots of equations that can't be solved algebraically. Let me start with some introductions. On the left of your screen, you see Sir Isaac Newton. On the right, this is Gottfried Wilhelm von Leibniz. These are the two men who, independent of each other in the 17th century, invented calculus. In fact, it's kind of a controversy for people who follow these things, because each of these men accused the other one of stealing his work. And it's kind of a beautiful comment on calculus, actually, if you think about it, because Newton was working in England and Leibniz in Germany, and they didn't communicate with each other early on. And just through their own process of thinking about math, they both invented the same concept. In fact, that makes me think that it really was a discovery, not an invention. Now, it's important to know both of these men because we can blame them for the annoying fact that calculus has a million different notations. In particular, the f prime notation is attributed to Newton, and dy dx is attributed to Leibniz. And for up to now, these two notations have really been interchangeable. But the truth is, at its core, Newton and Leibniz were thinking about calculus in really different ways. And Newton's ideas have helped us in a lot of applications. And later in this unit, in fact, in the next video, Leibniz's notation is actually going to become really helpful. Today, though, let's focus on Newton. So Newton invented a method for finding roots. And this is a really important thing. I'll try and convince you of why it's important using a simple question. The question in the box here says, where does the following function have a maximum? At this point in the course, that's a pretty easy calculus question. All we need to do is find the critical points and then use the first derivative test. But for this example, we get stuck. Can you see where we'd get stuck and why? Right, so maybe you took the time to work this out. Basically, if we find the derivative, that's pretty easy. And the next step, if we want to find those critical points, is to set the derivative equation equal to 0 and to solve for x. But that's where we get stuck. If you look at the equation on the screen, this is a cubic function, and it has 3 terms, so we would call it a cubic trinomial. And we don't have any strategy that you've learned so far in math to get x by itself. If this was a quadratic, if that said squared, we could use quadratic formula or maybe even snowflake method and get 2 factors and then use the zero product property. But if we can't factor it, and we really don't know how to factor cubics very well, there's nothing you can do. And that's crazy. We've kind of been lying to you your whole career. There are some equations that just can't be solved. Now, what you should realize, and what Newton realized, is just because we can't solve them algebraically doesn't mean they don't have a solution. It's going to be some decimal number. And so Newton wanted to find another way that wasn't algebraic, that didn't involve factoring, to figure out what the solutions would be to this kind of equation. The idea he came up with was a beautiful idea of critical thinking. He started with what he knew, and then he built on it. And it wasn't perfect, but because he was able to build on it, using these incremental ideas, he ended up with something totally brilliant. It all started with a very simple realization, something that you already know and probably take for granted, which is that the solution to an equation, like this one, is the same thing as the roots of a function. So here's a function. This side will equal 0 at these 2 x values. So if we can think about it graphically, solving an equation is really just finding the zeros of a function. And Newton didn't have Desmos, didn't have a graphing calculator to create the graphs. But since you do, can you think of a way to use the graphs to figure out what the roots are? Right, we could just read them off. So go ahead, can you tell me approximately what do you think the roots are of f of x, g of x, and h of x? Exactly. All we need to do to estimate the roots is look at the graph. This parabola, which is actually a cubic, we just can't see the whole thing, looks like it has a root somewhere between 2 and 3. And so I would estimate it to be 2.5 or something. This cosine function, which I only see a piece of, looks like it has a root between 0 and 1, and there are a number of roots here, one of which is between 2 and 3. Okay, armed with this simple realization, let's look at Newton's method. Newton's method is a way to estimate a root of a function, and we need this method because some equations can't be solved algebraically. What we're actually going to do is we're going to use tangent lines to make a series of guesses that get closer and closer to the true root. I'm going to show you this process, and I'm going to show you what you write algebraically and what is really happening in terms of the graph. But before we start, remember that Newton didn't have technology. So what was truly brilliant about his method is that you had to really believe in what was going on, because he could guess that we were getting closer and closer, but he couldn't actually see it the way that you're actually going to see it happen when I show you the graph. Example 1 says use Newton's method to find a root, and then it gives us a cubic function. Because this process is going to involve a series of steps that we repeat over and over and over again for new x values, start by setting up your work in a table format. Your table could look something like this. In the first column, we're going to guess what we think the root might be. And this little I just means that we're going to guess multiple times. And then in the second column, we're going to find the equation of a tangent line, a line tangent to the original curve at our guess. And finally, we're going to calculate where that tangent line crosses the x-axis. Where does the tangent line have a root? Okay, let's get started. So pretend you're Newton, you're looking at this cubic function, and you are guessing that it has a root somewhere, but you don't know where. If you were starting this process the way he did, you would just make a totally blind guess about what you think the root is. Maybe you'd guess 0. And since this is your first guess, I'm going to call that x sub 1. Now, you and I know in modern day that at 0, this function does not have a root at 0. But Newton didn't know that, so he had to guess. And what he did next was he found the equation of a tangent line at 0, which meant he needed to know the derivative of the original function, which I've just written up top because we're going to use it a bunch of times. And then he had to plug in the x value to the original function to get the y value of his point, and to the derivative function to get the slope. From there, he used point-slope form and just solved to get the linear function. This should look pretty familiar by now. And then came the really brilliant part. He took that linear equation and he figured out where it would cross the x-axis. In other words, where does the linear function have a root? Well, remember, a root is a 0. It's where the output of the function equals 0. And whenever we ask the question where in math, we're really asking at what x value. So solving this equation out, the root of the linear equation is at 2. Okay, so what's so brilliant? Well, Newton realized that even though we just guessed a random number, because the linearization, the tangent line at that number, has to be at least traveling in more or less the same direction as the real function, Newton proposed that the root of the linear function has to at least be closer to the real root than 0. And I can show you this using a graph. So we're not done with the process. We're actually going to come back and do another step. But let's take a pause for a second to see why Newton realized that 2 has to be closer to the real root than 0. So if you remember from earlier, this is what our function looks like. We started Newton's method by guessing that the root would be at 0. Clearly, it's not. The root's somewhere over here. And we quickly realized that probably wasn't the right root. So we went ahead and found the y value, which turned out to be 4. So we started out with this point, and I can graph the point here on Desmos, and you can see it here in the black dot. And knowing that that point probably wasn't the root, we found the equation of a tangent line that went through that point. The tangent line was negative 2x plus 4. Let me graph that as well. Here it is. And since the direction of the tangent line is close to the direction of the original graph, we then, in our last column, calculated where this tangent line would cross the x-axis. Visually, we were tracing the line down to find this number right here. And you can see, it's 2. That's why we got x equals 2 right here. And then, of course, this realization that Newton made. This is the important part. Newton reasoned that even though our original x value, 0, is really far from the actual root that I want to find, which is right there, this new x value, the x value that is the root of the tangent line, must be at least closer. And as you can see, this new x value right here really is closer to the root, which is the number we're trying to find right here. The question is it close enough? Well, if I zoom in, you can see it's still really not a very accurate guess for what the root should be. It's pretty good, but we can do better. Can anyone think of what we could do to get an even closer x value? So if you thought of an idea, you're brilliant. And Newton was brilliant. But frankly, part of what's so brilliant about his idea, and maybe yours, is that it seems totally logical when you see it done. Here's the next step. We're going to repeat this whole process using this new x value. We'll set up the algebra first, and then I'll go back to the graph and show you why. Go ahead and set up a new row. And take x equals 2 to be your second x value. We'll call it x sub 2, and it equals 2. My first step is to find the equation of a tangent line, again, tangent to my original function, at x equals 2. The calculations that we did with 0 were easy because we had 0. Plugging 2 into the function and the derivative is a little more tedious. So if you like, use your calculator. I recommend putting this equation into y1 and this equation into y2, and then using your table to plug in 2. If you don't know how to do that, come ask me and I'll show you some. And whether you use the calculator or do it by hand, you should see that when you plug in 2 to the original equation, you get 0.8, and when you plug in 2 to the derivative equation, which is right here, you get negative 1.2. From there, we write the tangent line for this new approximation. What line would that be? Exactly, the next linear function. And then what do we do with this new linearization? Right, we set it equal to 0 in order to figure out where it has a root, and we end up with 2.6667. Now, notice that I kept 4 decimal places. That's really important for the AP exam. In order for your final answer to be accurate with 3 decimal places, you always want to keep 4 decimal places in your process. So this was the second round where we made a guess and then we used a tangent line to get a better guess. Let's go back to the graph. And again, Newton couldn't have done this. He was just being brilliant in his head. But we can look at the graph to understand why this number is the best approximation yet. It's better than 0, it's better than 2. Turning back to the graph, in this row, we started out thinking about the point at 2.8, which is that point right there on the original function. We knew that 2 wasn't exactly right. We got 2 from the x value of the previous tangent line's root. And then we went up to 2, and we found a new tangent line way up there. The new tangent line, this one right here, you can now see in blue. And then the last thing we did was we found the numerical answer for the root of that tangent line, which, if we zoom in on our picture here, is kind of like taking the blue line and tracing it down here to where it touches the x-axis. What do you notice about the intercept of the blue line? Exactly. It's even closer to the actual root. So what if we wanted to get even closer? There's still a little gap there. What could I do really to get even one more step closer? Exactly. We're going to draw another tangent line, one that's going to get us even closer. And we're going to use this x value right here. We're going to go up to the graph and use that new point to find a last tangent line. Go ahead and see if you can do that. Take your last approximation. You're going to make 2.667 your third guess.